Swayam Prabha. Digital India. Educated India.
Okay, good morning to you. This is lecture 7 in the second module on review of basic structural analysis. We finished the first review where we covered statically determinate structures. Now we are going to look at statically indeterminate structures as well as kinematically indeterminate structures. The first 3 lectures in this part will deal with force methods as applied to statically indeterminate structures. You have already had an exposure to this in your earlier course, so I will go a little fast. As I mentioned earlier, we are going to refer to this book on structural analysis, part 4, statically indeterminate structures, force methods. You really have not had much exposure to displacement methods, but you have had some exposure to force methods. The most popular force methods are the method of consistent deformations, theorem of least work, which you have been introduced to, and these lead to a more generalized method called the flexibility matrix method, which we will study in depth in this course. And there are other methods like the column analogy method, which are good for manual use, but we are not going to cover in this course. We will look later at displacement methods, but at the very outset it is important to know the main differences between force methods and displacement methods. They are both aimed at analyzing indeterminate structures, completely different paths. Both are very interesting. Displacement methods are probably better suited for computer application, but can you tell me what are fundamentally the main differences between force methods and displacement methods? First, with regard to the type of indeterminacy. Static indeterminacy, which means you are talking about unknown elements in the force field, so that is part of the force methods. And in displacement methods, we worry about kinematic indeterminacy. Okay, that is one major difference. What else? Okay, so first the type of indeterminacy, which you have answered. Secondly, to solve the indeterminacy, you need to apply some equations, which are called governing equations. As you know very well, in force methods they are of the nature of compatibility equations, while in displacement methods they will be of the nature of equilibrium equations. And you need to express the unknown the displacements in terms of forces. You can do it 2 ways. You can either use a flexibility approach, where you deal with the flexibility matrix, or you deal with the stiffness matrix. So these are broadly the fundamental differences. As I mentioned, the first 3 lectures will focus on force methods, and the next 4 lectures will focus on displacement methods. Let us begin with something you know very well. Look at this pin jointed frame or truss, plain truss. What is the degree of indeterminacy? Static indeterminacy. Yes? 2, very good. Would you describe this, is it 2? Look carefully.
1 sir. 1 sir.
It's 1. Okay, it's 1. It looks deceptive, it's 1. Okay. Would you describe this as, and you can use the m plus r greater than 2j equation. For example, what is m? How many members are there? 5. How many support reactions are there? Possible? 4. 5 plus 4, 9. How many joints are there? 4. 4 into 2, number of equations available are 8. M plus r minus 2j is 9 minus 8 equal to 1. So this is a simple problem with 1 degree of static indeterminacy. Can you tell me whether this kind of indeterminacy is external or internal? external you say, and yes, you could view it as external. Which reaction here is indeterminate, vertical or horizontal? Horizontal. So the vertical reactions are determinate, and as an offshoot of this, remember, if such a plane frame were to undergo support settlements, let us say the support D goes down relative to support A, would you get any forces in the structure? You do not, because the vertical reactions do not really change, so they are known, they are determinate. What is indeterminate is the horizontal reaction, HA and HD. So you are right, you could treat the horizontal reaction, one of those reactions, say HD, as the redundant X, and when you release that reaction you get the primary structure, which is statically determinate, which is just rigid, and this is one way of approaching. Now let me ask you, can you also treat the same problem as internally indeterminate? Yes, so that option is also there. You could remove which member or cut which member? Any one of those members, not necessarily the diagonal, but a diagonal is what we normally do. So can you remove the member to get the primary structure, or should you cut it? Now, some textbooks mention about removing members, which is okay in one sense but inaccurate in another sense. You will find that that member, if you cut it, will have no force. If you remove it also, it will have no force. But if you cut it and you apply the unknown redundant as a pair of equal and opposite tensile forces as shown there, then you are also invoking the stiffness or the flexibility of that member, which would be missing if you remove that member altogether. So the stiffness of that member BD has a role in governing the answer of X. So do not remove members, you just cut them. When you cut them, you release the member, right? So we will examine this more carefully later. So you have multiple choices of indeterminacy here, and it is left to you whether to treat this problem as either externally or internally indeterminate. But there are some other types of problems, for example this, where the support reactions are very well known, it is externally statically determinate. Here the indeterminacy is internal, and if you put a cut anywhere, you will expose a shear force, an axial force, and a bending moment, and you have to apply them equal and opposite as shown here, right. We covered the theorem of least work in the previous class, and you are familiar with this. The first equation, dou u star by dou xj equal to dj, is Castigliano's second theorem, and usually dj will turn out to be 0, okay, and if it is so, then you can interpret this also as a minimization of the complementary strain energy in the structure. Now the dj that we are referring to here is a displacement conjugate with xj. If you look at the previous problem where you took the support reaction as xj, the horizontal reaction, then dj would be the movement in that support, and that movement is 0. So in that example, isn't it? The movement in the original structure is not allowed, so dj is 0. Similarly, if you have a situation as in the previous case where you treated the bar as redundant, what would dj refer to? I will go back to the previous problem. Yes, here what would d, displacement d, refer to at the redundant location? It will be the relative distance between the cut ends of the bar, okay. So you have to interpret it in that sense. You are applying two equal and opposite forces x to reflect the redundant. The conjugate displacement is the basically the elongation in that bar, which will be represented by the relative movement in that bar. Now since the bar is not cut, compatibility demands that the two ends should remain joined to each other, and there is no relative displacement between the cut ends, right. Actually the bar can elongate, d is not the elongation in the bar, it is the relative displacement between the cut ends, and that is how it is reflected in Castigliano's theorem, and the interpretation of it is that you are actually minimizing the strain energy. We demonstrated this with a simple problem of a 2-span continuous beam, if you recall, and you need to carry out this integration, and you will get x equal to 5w by 8. Now there is another way of doing the same problem, and that is the method of consistent deformation. We choose the same redundant x as the support reaction in the middle support, and then we release that reaction. How do we release it? By removing that support altogether, and so we do a superposition of that primary structure, which is a simply supported beam loaded with the external loading, in this case the UDL, plus the unknown redundant, now shown as a separate load case. So we treat x as a load but an unknown load, and our job is to find x. How do we do that? Equilibrium is not enough, you need to invoke compatibility. What would compatibility be here? What would be consistent? The deflection at B should be 0. So that is what you do, you look at the deflected shapes for a better understanding. In the picture on the left you can see very clearly delta B is 0. Here B, this deflection will be maximum, and so will it be here, but they are in equal and opposite directions, and actually you can calculate those values, you know those standard formulas. What would be the deflection due to the UDL here in the middle? 5 by 384, you can derive it as well, into W, not L, there is 2L coming into the picture, 2L the whole cube by EI, right. Similarly due to a concentrated load, it is x into 2L the whole cube by 48 EI. These two should be equal, that is compatibility, and when you invoke that compatibility, easily you get the answer, x is equal to 5 by 8 times W. Is it clear? This is a nice way of doing it, and you understand the meaning of consistent deformations. Is it clear? So we are going to explore these two approaches. One is an energy approach where you minimize complementary strain energy, but mind you, the theorem of least work is strictly applicable only when you do not have support settlements, only when you have dj equal to 0. But if you had support settlements, you could still invoke the energy method, but you are basically doing method of consistent deformations, you are just finding displacements using an energy formulation. So if you want to complete this problem, after you have got the answer x equal to 5 by W8, you can superimpose the free bodies and you get the two bending moment diagrams. The first, due to the load, is causing a sagging moment here, it is causing a hogging moment here, you join these two, you get a diagram like this. Okay, it is very straightforward, you can draw your shear force diagram and so on. Now let us summarize the basic concept underlying force method. What is the first thing you need to do in the force method? Identify the redundance, which also depends on the degree of static indeterminacy. So find the degree of static indeterminacy and choose, and you have choice here, choose your redundance. If there are n subscript s stands for static indeterminacy, then you have to choose as many redundants as the indeterminacy demands. Next, what do? Once you have chosen the redundants, you have also chosen, no, you have also chosen the primary structure where those values of x are 0, where you release those constraints, right. And on that primary structure, what should you do? You first apply the external loading, and then you apply the redundants one at a time if you wish, and write down the governing compatibility equations. Okay, so wherever you have made those releases, write down those expressions. Usually D1, D2, D3, D4 at those redundant locations will be 0, but there are some exceptions. Okay. Where they are 0, you have a choice of invoking the theorem of least work, but otherwise you have to actually calculate the, let us say the support settles or moves horizontally, then dj is equal to that movement. Is it clear? Okay. Express the equations using a flexibility format. Which equations? The compatibility equations, and you have choice here, and then you solve these simultaneous equations and find x1 to xn. Once you found x1 to xn, if you draw the free body, you have got a statically determinate system. You can analyze it, draw the shear force diagram, draw the bending moment diagram, or find the actual forces in the case of a truss. You could do it directly on that overall free body. Alternatively, you could find out what is happening in under the action of each of those loading systems on the primary structure and superpose everything. And so you find the complete force response. It satisfies equilibrium, but more important, it also satisfies compatibility. Let us quickly look at a broad generic way of describing this method. I have given you in this a 3-span continuous beam subjected to some arbitrary loading, and on top of that we have got some support movements. Support A, which is a fixed end, is shown to rotate by a known amount theta A, it is a rotational slip, and support C deflects by delta C. The degree of the static indeterminacy of the structure is 3. So you have many choices of the primary structure. Which one would you prefer? Cantilever, it is easiest to draw. So good. So you remove all those 3 supports and you can basically identify the reactions as x1, x2, x3. Now one would imagine those reactions will be pointing upward, but there is a good reason to assume them to be pointing downward for calculation purpose. I will show you the reason in a while, and then they turn out to be negative, which is totally acceptable. Now this is your primary structure. You have released the constraints at B, C and D. You have got a cantilever, and this can deflect, and the deflection that you get at B conjugate with your chosen coordinate 1 is D1. Deflection at C at downward is D2. Deflection at D downward is D3, right? Now you know the answers to D1, D2, D3. They are not 0, not all of them are 0. What is D1? D1 is 0 in the original problem. What is D2? Plus delta C. And what is D3? 0. So these are your governing compatibility equations. These are what the right hand side of those equations should look like. Okay, 0, delta C, 0. Right. Now you take the primary structure and do a series of superposition. You have 2 loads here, please note. One is called direct loading. The external loads are directly caused by those arrow marks that you see there. Some are forces, some are moments. There is a concentrated moment shown there. You also have another kind of loading here. What is that loading called?
Support settlement.
Yeah, that is called indirect loading, in this case by support settlements. These two you should be able to put on your primary structure. The loading, the direct forces are pretty easy to do. You can analyze this, can't you? And you have to find the deflections D1L, D2L, D3L. The L here stands for the loading, the external loading. Is it clear? So at those locations 1, 2, 3 where the redundants operate, you must be able to find D1L, D2L, D3L. You know enough techniques for finding deflections. Any method you can use. We will use the unit load method because it will help us generate the flexibility matrix very easily in a generic fashion. Then you take the same beam and now you apply support settlement. What will it look like? What will it look like?
Rigid body movement, rotation.
It is a rigid body movement. See, of the 2 support settlements, support movements shown in the original figure, delta C is accounted for on the right hand side of the equation. You understand? Delta C is occurring at a redundant coordinate. but theta A is not at a redundant coordinate, it is at a non-redundant coordinate, right. So that you apply as a load, as an external indirect loading on the primary structure. If you allow that beam, that cantilever beam to rotate by theta A, it will undergo a rigid body rotation, and we are assuming very small deformations. So sin theta and tan theta are equal to theta. So can we write down those additional movements at 1, 2 and 3 as shown here? This is easy to understand. Theta A into L1 is the movement here, and so on and so forth. Can we work them out? So you have got all the movements caused by the external loading on the primary structure. Now you apply the redundance. Let us put them all together in the beginning. You apply x1, x2, x3, and let us say the deflections that you get at 1, 2, 3 are d1x, d2x and d3x, and now you are in a position to write the equations of compatibility. What would they look like? They will look like this. In general, you may have n locations, n displacements, n degree of static indeterminacy. So what I have written here, the first vector, first column on the left side is the deflections that you get by the direct forces on the primary structure, which is what we showed here. Next are the additional deflections which you get in case you have indirect loading at non-redundant locations. If you have displacement at redundant locations, they get covered on the right hand side here, they get covered here, not here. Is it clear? Then we are putting together all the deflections caused by the redundance on the primary structure. Now you see how your learning has progressed. You first studied force response in statically determinate structures, then you studied displacement response in statically determinate structures, and you need that understanding to write these expressions in the compatibility equation, because you are still dealing with a statically determinate primary structure. Now you will find it convenient to apply one load at a time according to the unit load method. Now you are familiar with the definition of flexibility. So I have shown here 3 diagrams, 3 cantilever beams, they are all identical beams, but I apply x1 equal to 1, x2 equal to 1, x3 equal to 1, not all at the same time but separately, and the definition of the flexibility coefficient is that the deflection here caused by x1 equal to 1 is called f11, this is f21, this is f31, this caused by x2 equal to 1 is f12, f22, f32 and so on and so forth. Is it clear? So this is a physical meaning, and you will find that these flexibility coefficients are properties of the structure, they do not depend on any loading. How do you find these values? Unit load method, and you can generate a nice formula, that is integral mj mk by ei into dx, right. This is unit load method, and you can do that and you can write it in this format. So all the deflections caused by all the redundants put together can be written like this. So d1x is f11 into x1 plus f12 into x2 etc plus f1n into xn, similarly d2x and so on. So I can write that overall set of equations, and also I get the deflections caused by the load using the unit load method. So the beauty is whatever unit bending moment diagrams that I drew for this and this and this come in handy when I find these deflections, right, because if I want to find d1l, I need to apply a unit load here, you understand. So this bending moment diagram caused by this is called m1 and so on and so forth. So those moment diagrams come in here. So you need how many diagrams? You need one moment diagram which I call ml caused by the external load on the primary structure, and I need separate diagrams caused by xj equal to 1, x1 equal to 1, x2, which I call small m 1, 2, 3, 4. With the help of these diagrams, and if you want to do it manually with area multiplication method, I can get all the answers. We will see later in matrix methods, you do not have to do this manually, you write a program which will generate everything automatically. So I can now write my compatibility equations like this, right. I am writing all the expressions, and in this particular problem where I have only 3 unknowns, I can write that equation, then I can solve for x1, x2, x3 by inverting that flexibility matrix or using some elimination method and then solving it. Once I have the solution for x, I have got the correct force response, I can draw my bending moment and shear force diagrams on my overall free body. Is it clear? This is a broad method, we have done this. I will go quickly over an example which we have done earlier. This is a 3-span continuous beam with a cantilever overhang. This is familiar to you, we have done this? Yeah. Okay, so here what would be a good choice of redundance? What is the degree of indeterminacy here? 2. Which 2 would you choose? Well, you can choose. You can choose any 2 reaction. Okay, you said B and C because you are more comfortable with a simply supported beam where the supports are wide apart. But let us do something contrary to that. Let us choose the reaction at A and D as the supports. Okay, there is nothing wrong with that. Of course, it's you are right, this is not a good structure to build because you will have very large deflections at A and D. But mind you, you are not building the structure in real life, you are just building it in your mind and just for the purpose of solving this problem. Okay. So you can straight away write the compatibility equations based on what we discussed. You have only 2 unknowns here. Do you agree these are the correct equations? On the right hand side, D1 and D2 are both 0 because you do not have any support settlements in this problem, right. Then your primary structure is one where you released the supports at A and D. These are the deflections caused by the external loads, agreed. I removed the support at A and D and I let it deflect under the external loads. This deflection in this direction matching this assumed direction of x1 is D1L and this deflection is D2L. Do you know how to calculate D1L and D2L? How will you do that? First you have to get the bending moment diagram for this loading, then you have to apply a unit load F1 equal to 1 at A and separately F2 equal to 1 at D, analyze those, which is what we will do. So in the first case you apply x1 equal to 1 and incidentally when you do that, this deflection that you get here is F11 and the one that you get here is F21 and you can do the same with F2 equal to 1 and you have to now solve and get the equation. In other words, we now need to fill up this matrix which is a coefficient matrix and we need to find these values and then we can find x1 and x2. That is it, straightforward, the concept at least. Now the problem with this beam is you have a bending moment diagram which is made up of not only straight lines which are easy to handle, but you also have a parabola coming into play. So it may be convenient to split it into 2 for the purpose of calculation. Okay, so here I have done that. I just took the UDL part and drew the bending moment diagram due to the UDL separately here, which you can recognize, and the rest of the loads, the 3 concentrated loads, would give me a bending moment diagram like this. You will notice both the diagrams are hogging moment diagrams because the overhangs are really making the beam hog. The deflected shape also reflects the hogging. Clear? Now the other one is easy to do. When you apply x1 equal to 1, the bending moment diagram, small m1 diagram will look like that. When you apply x2 equal to 1, this is what that diagram will look like, right. Let us not worry too much about the calculations, you know how to do this, but conceptually once you have got these diagrams you can multiply these diagrams the way we did in the earlier classes and get the answers. For example, if you want D1L and D2L, you need to do that integration and these are the answers. If you work them out, they are solved in the book, you can study it in detail. We have done this last year, so you are familiar, and you can find F11, F21 which is equal to F12 and F22. They are pretty straightforward and you can get these numbers. You plug them into the equations and these are very easy to solve in your calculator. You can invert the matrix or directly solve it. You get x1 and x2. You will notice they come negative, right? They come negative and so you interpret it as the forces acting upward. Now the reason why we assume them to act downward in the first place is you will find that all the bending moment diagrams have the same sign in general. So you do not have to worry about signs when you multiply. The negative into negative turns out to be positive. That is the main advantage. And you can draw the free body diagrams. Once you know x1, x2, you can do this. You can draw the shear force diagram, draw the bending moment diagram. This is the least expected from a student at this stage. That means you have learned how to do statically determinate structures, you have got a statically indeterminate structure, you found the redundants, and after you found the redundant, the structure is reduced to a statically determinate structure and you can handle any structure. We have shown a beam, but you could very well apply this to a truss frame. Now usually it makes sense to handle support settlements as a separate analysis problem rather than mix them along with the direct forces, because you would like to know out of curiosity how much effect this has independently. Now here is the same beam, same continuous beam, where you are given that the support B has settled by 5 mm and the support C has settled by 10 mm. Mind you, the same flexibility coefficient which you calculated earlier are applicable here, so you do not have to do any extra work. You just have to write the equations correctly. We will choose the same redundants and now we apply. You will find the 5 mm and 10 mm have occurred at the non-redundant locations. So you have to treat it as a load. So you take the primary structure and you allow these movements to take place, you will find you will get a nice straight line rigid body movement, and from this movement you can figure out what is delta d1l and what is delta d2l. Can you work it out? What is delta d1l? Well, the whole beam rotates by an angle theta and the relative displacement at B and C is 5 mm. So you will find this angle is this difference, which is 10 minus 5 divided by the span 3.75. This 10 minus 5 in millimeter you have to convert to meters, so it is 0.005 by 3.75. That angle you need to use that to figure out those two movements, which is simple. You can easily do it using logic and get the two deflections correctly with the proper sign. You will find that delta d1l turns out to be negative, whereas delta d2l turns out to be positive. If you made a mistake here, you will get wrong answers. So you have to get this correct, and after that same old equations. Only thing here you have, instead of d1l you write delta d1l because this is the one caused by the loading. Supposing you have a problem in which you have both the external loading and this, then you add those two quantities on the left hand side. That is it. F1, F2 is all known. Solve this equation, you get x1 and x2, and then you can draw your free bodies, shear force diagram, bending moment diagram, and deflected shape. Is this clear? Conceptually it is very straightforward. If you take the example of a truss, here you have a truss with how many bars? 10 bars. Is it statically determinate or indeterminate? It is indeterminate. What is the degree of indeterminacy? Well, one look at that structure should tell you. First look at external indeterminacy. Externally you can view it as being, it is not simply supported, so you got one extra redundant. If you make it simply supported, that means release a horizontal reaction. So one external indeterminacy. Internally you got an extra diagonal. Can you see that? So you can choose. So that is what you do. So you can choose one of those diagonal forces as one redundant and a horizontal reaction maybe at D as another redundant. So your primary structure will look like this. Clear? You have made a roller support at D and you cut the bar 10 in this case, and the forces, if you want to insert them, will be x1, which is the tension in that bar 10 which you do not know, and the horizontal reaction we are calling x2. Is it clear? Now write down your compatibility equations, they take the same format, it is very easy to write them down, and on the right hand side d1 and d2 are 0. When you say d1 is 0, you are actually making a statement that the relative displacement between the cut ends is 0. The bar should never have been cut in the first place. We are not saying that that point is not going to move, it will move when the bar elongates or contracts, but we are saying the relative movement is not there, right. So those double arrows pointing each towards each other refer to relative movement when you interpret from a displacement perspective. Now physically it is a little troublesome, because if they really approach each other they will kind of penetrate each other or overlap each other, but that is something that you worry about in your mind, okay. They can separate out or they can penetrate, is it clear? That is the meaning of that. Okay, so you can also use strain energy formulation and solve the same equations, they mean the same thing. And how do you calculate the displacements? You can use a unit load method, I hope you are familiar with this. Apply x1 equal to 1, get those forces, apply x2 equal to 1, get those forces, and so on. So if you do that, so I have got 3 diagrams here. The first diagram is the structure in which I apply only the external loads, the primary structure. The second one, I apply x1 equal to 1 and I solve it by method of joints or method of sections. In the second one, I apply x2 equal to 1, right. When I apply x2 equal to 1, x1 is 0, so this bar has 0 force, this bar has 0 force here as well, here this bar has a force of unit magnitude. When you analyze this, we have done this last year, so I am going fast over it. It will be nice to write it in a tabular format. Write down the 10 bars, note their lengths, write down the flexibility which is L by EA. So the length of each bar is known, the EA values are given to you, and analyze those 3 trusses and write them down. And if you take this particular case, it is so easy, there are only 3 bars. When you pull here horizontally, you will have an axial tension in these 3 bars and you do not have any force in any other bar. So that is why this is just 1 1 1, all the others are 0. Is it clear? So these things should not take you too much time. Once you have done this exercise, invoke your unit load method equations. Are you clear about this? We have done this before. So get those numbers in terms of EA, and EA gets eliminated, substitute in your compatibility equations and solve for x1 and x2. The final bar forces are given. You can do superposition, you have already solved in that table, you have got those forces, you have got force caused by external loading, you have got force caused by x1 equal to 1. So take that column, multiply by x1, take the next column, multiply by x2 and add up everything and you get the answers, okay. Now it is interesting to note that some of those bar forces will be positive and some will be negative, you must be able to judge correctly. For example, in that particular loading, you would expect the bottom chord to be in tension, the top chords to be in compression, and the verticals and diagonals appropriately you should figure out. Now let us take a displacement loading problem. Let us say you have a lack of fit problem, bar 10 is too long by 3 mm, okay, too long by 3 mm. So when it came to the site, that bar was too long, so it had to be forced fitted, that means it had to be hammered into place. Now because the structure is over rigid, all the other bars will resist this fixing. Had it been just rigid, they will move and accommodate this movement. Now you have a problem, you are forcing that bar to be fitted. First of all, can you tell me what will be the force in that bar? It will be compression, because it was too long, it will not be allowed to get that length of 3 mm. The final length, excess length may be 2 mm or 1 mm, it depends on the relative stiffnesses of all those bars, right. And because of this, the other bars will also be stressed. and so you have a self equilibrating system. How do you solve this problem? Well, let us take the same redundance as we identified earlier, and now the compatibility equation will look like this. Is it clear? Because now you have a displacement loading. How will you get delta d1L and delta d2L? This is not as easy as the previous problem where you had a rigid body movement in your beam. How will you find this out? What is delta d1L and delta d2? What does this physically mean? In which structure? In which structure? In which structure? In the primary structure. So take the primary structure where you have a roller supported D and that bar 10 is cut, and then you allow this bar 10 to be too long by 3 mm. Will you have any forces in the system? No, because it is just rigid, it is statically determinate, you will have no forces. Now can you write down delta d1L and delta d2L? Delta d1L, what will it be? What will delta d1L be? It will be 3m, it is free to take whatever length you want it to take. So it will be plus 3 mm or minus 3 mm? Plus 3 mm, it is too long, so it is plus 3 mm, clear? What is delta d2L? Delta d2L is 0, right? Now this 3 mm you should write in a consistent unit, so it is 0.003 meters, and if it is too long you should visualize this as an overlap of those two bars by 3 mm. Is it clear? So that is all you have to do. You have already got the flexibility matrix in the previous examples, so you just have to plug in these values.
So why are we not taking D1 as 3 mm?
Okay, this is a good question. What is D1? D1 is the final displacement in the original real structure, not the primary structure. And when you identified x1 as the axial force in that member, and your primary structure was a structure in which you cut that member, D1 is nothing but the relative displacement between the cut ends. What is the relative displacement between the cut ends? It is 0. So these are the typical mistakes students make. I want absolute clarity in understanding here. D1 is always 0 because it is a relative displacement between the cut ends. You had no business to cut that bar, right? 3 mm is the elongation. You can visualize the elongation in that bar in a statically determinate system, which is the relative distance between the cut ends in the primary structure. So when you are talking about primary structure, you are not talking about the right hand side, you are talking about the left hand side, because all these quantities on this side of the compatibility equations, that is all these values relate to primary structure. Is it clear? This is a common mistake we tend to make, and D2 is always 0, so you do not have to worry. So isn't it easy to solve? You have already got the flexibility matrix, you have already inverted it earlier, and so it is very easy to solve. You get x1, x2. So once you are familiar with a truss and its flexibility matrix, you can handle any loading. You put 100 loads, you get 100 answers just by solving this matrix, and once you have the solution, you can do superposition, you can get the forces. And what is interesting is you must check the answer. The bar 10 you suspected would be in compression, and it does turn out to have a negative value here, so it makes sense. If it goes into tension, then you made a big mistake. So you must have these checks into your mind. One last problem in continuation with the previous one. Supposing you have temperature loading, okay, and I am now saying 3 arbitrary bars, 1, 2 and 3 are subject to a temperature increase of 40 degrees Celsius, and the coefficient of thermal expansion is given to you. How would you now deal with the same problem? this is your problem. Okay, you can remove that 40 kilonewton. How would you analyze this problem?
The elongation caused due to temperature.
You have to figure out in the primary structure what, so you need to, you agree your right hand side D1 and D2 are 0. How will you get delta D1L and delta D2L?
Delta D2L is 0. Delta D1L is caused due to this.
Okay, why do you say delta D2L is 0? You are right.
It doesn't move.
It does not move for what reason? Okay, how do you get delta D1L? Let us say we do not make any guesses, we do it the hard way. How do you get delta D1L? Now the difference between this problem and the previous problem was, here the previous problem you had a movement in the redundant coordinate. This one you are having movements in non-redundant locations, like bars 1, 2 and 3 are not at the coordinates 1 and 2. So in your primary structure, which is one with a roller support and with the bar 10 cut, if I heat bars 1, 2 and 3, can you tell me what those movements are? How do you find them out? You can invoke the unit load method, isn't it? You can invoke the, if you want to find delta D1L, what should you do? You apply F1 equal to 1, so you do that. But first you, in your primary structure, if bars 1, 2 and 3 elongate, you have to find out those elongations. So which is nothing but L alpha into delta T, that is a straightforward calculation, right. If your alpha is this and your delta T is 40 degrees and your L is this, you can figure out what is E1L, E2L and E3L, that is straightforward. Then what do? You invoke the unit load method, which is, in this equation you apply say F1 equal to 1 or X1 equal to 1, and you look at this displacement field where you have these temperature changes and you have these known bar elongations. So you have a pure geometry problem and you are applying a unit load and invoking the virtual work method to solve for one unknown in that displacement field. We have done this in an earlier class. So can you find this out easily? You can. When you can do that, you have all the answers. You have the forces caused by x1 equal to 1, you have the forces caused by x2 equal to 1, and you will find that delta d1l, in this case it's easy to work it out. Delta d1l you can solve and you can sum up. You will find that only these 3 bar forces you need to worry about, because all the other e's are 0. So you have 3 bar forces, you can multiply them and get the answer. They turn out to be equal to 0.6, so it's easy to work out. So delta d1l you get. Delta d2l, as he guessed correctly, will turn out to be 0 for the simple reason that when you pull here, you only these 3 bars get a unit load, unit force, and these bars don't have any force. So you're multiplying a non-zero quantity, which is your bar elongation, with a 0 quantity, so you end up with 0. So you can guess this or calculate it. This is how you deal with non-redundant displacement. So we are trying to tackle conceptually different types of problems, and you can substitute these values, get your unknown forces, do your superposition. Here again bar 10 turns out to be compression. Let us look at one more example of a frame. You have a portal frame. We have done this also earlier. What is the degree of indeterminacy? Well, normally 3, but there is a symmetry in the frame, right? So can you reduce it? You can reduce by 1, you are right. So for example, what do you know for sure? Vertical reactions are statically determinate. You should never be thinking of indeterminacy for the vertical reactions. This will be the deflected shape. There is a symmetry in the deflected shape because the structure is symmetric, loading is symmetric. Your vertical reactions are total load. What is the total load? 200 kilonewton plus 15 to 3, that's
350.
350.
15 to 16.
15 to 6, right. 500 divided by 2 is 250, 250. Vertical reactions are determinate, but your horizontal reactions are not, and your moments are not, but they are equal and opposite. So you have only two unknowns, right. You could do this. If you do this, if you have to release all those movements, that means you must allow for a relative movement along x1 and relative rotation along x2, which means you must replace those fixed ends with roller supports. Is it clear? And because it is all symmetric movement, then the total horizontal movement, which is d1, will be divided by 2, so it is d1 this is d2, so d2l by 2, d2l by 2, and this rotation here is d1l by 2. Is it clear? This is one way of doing it, but you can also cut it in the middle at C, and the appropriate boundary condition would be a guided roller support. Why? Because it is free to deflect there is no shear transfer possible there. When you cut it into two, that constant load 200 kilonewton should also get cut into two. 100 kilonewton comes on the left side frame and 100 kilonewton on the right side frame. Here clearly there are only two unknowns, you can make it into a cantilever. So there is another way of doing it. Whichever way you do it, these are your compatibility equations, and let us take the first way. Can you find those movements? Well, draw the bending moment diagram, capital ML diagram. The concentrated load gives you a triangular moment, the UDL gives you a parabola, and then this is your small m1 diagram when you apply x1 equal to 1, this is your small m2 diagram when you apply x2 equal to 1. You do not even need to mark those deflections, they are just to help you understand. You can blindly go ahead and calculate d1l, d2l, f11, f22, f12. Once you have those unit loads, it is pretty easy to calculate. Okay, so we have done this earlier, so the method is straightforward. Write down your compatibility equations, solve for x1 and x2, draw your free bodies, draw the axial force diagram, the shear force diagram, and bending moment diagram. We will later do the same problem by displacement method, and I will show you it is much easier. You can do it in a couple of minutes and get the bending moment diagram directly. This is what the deflected shape looks like. So we will stop here, we will take this up in the next class. Thank you.